Okay, so in this video we're going to start talking about Unit 4, which is over Newton's laws of motion and forces. And so, like I said before, the past couple units have been more about kinematics, which has to do with the study of how motion occurs without regard to why the motion occurs. And so now we're going to talk more about the why, which has to do with forces and different types of forces and Newton's laws of motion, which you may or may not have heard before. Okay, and so before we actually get to talking about Newton's laws of motion, we just need to introduce a few terms. Okay, and so let's talk about some of the basic stuff. Okay, so here are just some definitions that you need to be aware of. Okay, and so the first one is called inertia. And basically what inertia is inertia is an object's resistance to changes in motion. Okay, so an object that has more inertia, that means it's more difficult to change the object's motion. Okay, either to get it moving if it was at rest, or if it's moving, to stop it from moving, it's more difficult. Now, the way we actually measure inertia is through what's called mass. Okay, so we have inertia, which is basically how much an object resists the change in motion, and we use mass to measure that, to quantify that. Okay, so mass is a measurement of an object's inertia, and mass really has to do with the amount of matter making up an object. Okay, now the symbol for mass is typically a lowercase m, and the unit for mass is kg, which is the kilogram. Okay, so 1 kilogram is 1,000 grams. That is the standard unit for mass. And so let's say I have a mass of 100 kilograms. The way I would write that is I might write like m equals 100 kg, where kg is kilograms. Okay, and so again, that's how you quantify inertia. So let's say I have two people. One has a mass of 100 kilograms. One has a mass of 200 kilograms. Okay, the one that has a mass of 200 kilograms would have more inertia, meaning it would be more difficult to change the motion of that person. Okay, so we have inertia, we have mass, which is how you quantify inertia, that's measured in kilograms, and then the star of this unit is force. Okay, and so what is a force? Well, a force is simply a push or a pull which is capable of accelerating an object. Okay, and there's lots of different types of pushes and pulls in the universe. We'll talk about some of those later on. For right now, the symbol for a generic force is a capital F, not a lowercase f, but a capital F. Okay, now there's different types of forces, and so we might use subscripts to denote different types of forces, but the overall symbol for force is an F. Now, what does that mean, subscripts to denote different types of forces? Well, kind of like how when we talked about velocity, we had Vf for final velocity, and we had Vi for initial velocity. Those tiny little letters in the bottom right, those are subscripts. Okay, and so I might use F for, any old force, but if I want to talk about a specific force, let's say the force of friction, I might write F with a lowercase f. Or let's say I wanted to talk about like the force of gravity. I might write F with a subscript G. Okay, or what if I had like an electric force? I might put Fe for electric force. And so there's lots of different types of forces in the universe. They all have the symbol F, but we use little subscripts to distinguish between different types of forces. Now, the unit for the force is the Newton. Okay, it is named after Isaac Newton, the guy who basically, came up with all his laws of motion and the law of gravity, and plus he also invented calculus, and he studied optics, and he did lots of crazy stuff. One of the most famous scientists of all time, for sure. And so that's why we name the unit for force after him. Okay, so the unit force, because it's named after a guy, it is capitalized. That is a capital N. So let's say I push or I pull on something with a force of, 50 newtons. I would write F equals 50, okay, and then a capital N to represent Newton. Now we'll talk more in a second about how much force that actually is, but Newton is the unit for force. Okay, so I would encourage you to pause it here and make sure you add that to your notes. Okay, so moving on. Okay, so before we get too far into it, I want to talk about an important distinction between weight and mass, because weight and mass are not the same thing, and a lot of people actually use them interchangeably even though they're not the same thing. And so now let's talk kind of about the difference between mass versus weight, and then I want you to watch a video talking about the difference between mass and weight. So here's the difference. Okay, the mass of an object basically measures how much inertia that object has. That essentially comes down to how many atoms are making up that object. Okay, mass has nothing at all to do with gravity. Okay, if I go to the moon and I'm on the moon, I still have the same amount of inertia because I still have the same number of atoms making up my body. If I just sit out there in space, okay, I still have the exact same amount of inertia because even if there's no or not very much gravity in space, I still have inertia. Okay, so if you took the 100 kilogram person to space and the 200 kilogram person to space, if you gave them the same push, the one with a mass of 100 kilograms would move, faster away from you. Okay, so mass has nothing at all to do with gravity. Gravity, the force of gravity is what we call weight, and so I'm going to write that down. The weight of an object, weight is a force, and actually we will label that Fg for force of gravity. The weight of an object does depend on gravity. It's in the name, force of gravity. Okay, that means you weigh, not weight. Let me fix that spelling mistake. You weigh different amounts on different planets. So for example, if I'm here on Earth, let's say I have a mass of 63.5 kilograms. That's like an average, mass for a person. Here on Earth, let's say I weigh 140 pounds. That's 623 newtons. If I go to the moon, I have the same amount of mass because I have the same amount of inertia. The number of atoms making up my body has not changed. But my weight is now 23 pounds or 103 newtons because gravity is not pulling on me as hard on the moon. On Jupiter, I would weigh 353. On the sun, I would weigh, almost 4,000 pounds because the sun has really immense gravity because it itself is very massive, but my mass would be the exact same. Okay, so mass has nothing to do with gravity, weight does. Mass is a measurement of inertia that's measured in kilograms. Weight is the force of gravity that's measured in newtons. Okay, so make sure you understand the difference between mass and weight. So I'm going to link a video about mass versus weight so that you can watch that video, and then we'll just talk about a few more things. Okay, so moving on. Okay, now, by the way, if you want to know what a Newton is, just to give you a sense for, I told you before that Newton is the unit for force, and weight is a force, and so how much is a Newton weigh in terms we might understand? So just to give you an idea, if you think of an apple is about 100 grams. It's about 0.1 kilograms. Okay, and so a normal apple has a weight of about 1 Newton. Okay, a person might be, 5 or 6 or 700 newtons. The force on a jet pilot during takeoff might be, a couple thousand newtons. But this slide right here is just to give you an idea of how much is a Newton in units of force, which is something that you can maybe relate to a little bit better. Okay, so when we're doing a problem and I say the guy has a weight of 660 newtons, just to put that in context, 660 newtons is only about 150 pounds. Okay. All right, and just one more quick thing about mass versus weight. Most of this we've already talked about before. I do want to briefly mention that there is an equation to calculate weight. We will come back to this later in this unit when we do more with calculations, but there's not a lot of equations in this unit to begin with, and so this one is kind of important to know. And so the weight of an object, if we want to calculate, as long as you're close to the surface of a planet, the equation for weight is this. This is one of our only two equations in this unit. Fg, which is the force of gravity, which is weight, right, that's measured in newtons, is equal to m, which is the mass of the object, multiplied by g, and remember, g is the acceleration due to gravity. Okay, and on Earth, the approximate value of the acceleration due to gravity is negative 10 meters per second squared. Okay, now it's important for you to know, by the way, that this negative only indicates direction. And so later on when we're doing calculations with weight, you'll see that weight, when you calculate using the equation, comes out to be a negative value, but the negative sign only indicates that the force of gravity goes down because gravity pulls things down. Okay, and so basically if you take the mass of an object and multiply by the acceleration due to gravity, you see that basically gives you the force of gravity, which is weight. Okay, and so when I go to the moon, my mass might be the same, but the acceleration due to gravity on the moon is not negative 10 meters per second squared. It's more like negative 2 meters per second squared. And so that's why I would weigh less on the moon, even though my mass would be the same. Okay, so this video is just kind of like an introduction to Unit 4. In the next video, we'll talk more about Newton's first law of motion. Okay, as always, please let me know if you have any questions, and I'll see you guys in the next video.